Okay, it's late at night. I got a bit of insomnia. Can't sleep. So what do you do when you can't sleep? I make a video for flat earthers. So there's a number of things they tend to get wrong. Let me go to Sargent. And here's the latest video they made.
Right, and so it never...
And I'm going to address this to DJ Curious. And the reason why is he claims to be a Christian. So given that, one would think that he kind of reveres the Bible and has a high regard for truth. Let me see if I can find my Bible verses here. Here we go. Look at truth. And so we have 192 occurrences of that. Let's jump down here and look at the New Testament, 2 Timothy through Revelation. And we see that it seems like God values the truth. Let's not live but indeed in truth. Little children, let's not love with word or tongue, but indeed and in truth. So doing good things and telling the truth. And so truth is something that's so valuable that some people call themselves truthers. In fact, flat earthers tend to think we're the truthers. So, and we have, let's look at iron here. Iron, I think it's Proverbs here. Go down here, Proverbs. Iron sharpens iron. That's the idea. So one person sharpens another. One person sharpens another. So if you want to seek the truth, there's another verse, one man seems right to another man speaks. So let's discuss this and see who in fact is telling the truth and who is promoting a falsehood. So given that, I'm going to go to my PowerPoint charts. One of the things is pressure, air pressure. Here's the earth, here's a section of it. Whether it's flat or round, a small section is going to appear kind of flat. You know, this is maybe a few hundred meters, a football field here. So we're going to look above this football field. And we see, here's air molecules, and this is notional. There's zillions of them, not hundreds or dozens like I'm drawing. So air pressure is density. Air pressure is the gas laws. I have that up here somewhere. Let me see if I can find that. Real versus ideal gases. Yeah, it's right here. So we have ideal gas laws and non-ideal gas laws. So here's the simple form for ideal gas laws, but it gets a lot messier if you. And here's if you look at the curves here. Here's the curve for ideal gas, pressure versus volume. But non-ideal gases, you could look at that. You could Google this. Just the thought is, have to consider other things like the size of the molecule and that. So going back to that previous chart. There's a sweet spot where the ideal gas laws pretty much match the real gas laws. But if you get really low, high pressures, really high pressures, or really low pressures, like this is out in space. When you go out in space, or if you go super high density pressures, it deviates. So where we live, the Earth, it's kind of near the sweet spot. So you could kind of use ideal gas laws and they work pretty good. So that's important to know. So now let me go back to my chart here. So here it is. So down here, you can kind of use the ideal gas laws. But when you get up right here, space, you got to use the real gas laws. And one of the reasons is it's just now these molecules aren't static, they're falling. So like Mark Sargent was a pinball champion, so just imagine this is a pinball machine. Let's just take this one air molecule, say O2, and it's going to bounce off here, then it's bounce, bing, 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 bing. It's going to be binging a lot faster here. Bing, 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 bing. Up here, when it falls, it's going to take a trajectory. It's like you throw a ball in the air, goes up, and it's going faster here. It slows down. Where here, it's still moving this way, the same speed, but as far as up and down motion, it comes to a stop for an instant, then it comes down, it picks up speed again. But just now, let's move this into here, and you launch this gas molecule up. It's going to bing, bing, bing. It's not going to take this trajectory. It's going to just be bouncing around here. But let's say we boost one gets boosted way up to here. It's going to travel a longer way before it hits anything. And that's why the ideal gas laws doesn't really work. The ideal gas laws assume it's always going to be bouncing and hitting, banging off things. That's what's called pressure. Pressure is when, like here's our container, when the molecule hits against the wall and bounces off, that puts pressure on that wall. And if there's more of these inside than outside, or they have more velocity, or there are more of them, they hit more or they hit harder, they're going to make this, you're going to push, try to make this thing expand. They'll be pushing against it. But on the other hand, if there's more outside, higher pressure, or they're faster, there's going to be a net push that's going to try to collapse the pan. So then it's like, where's the line between space and the vacuum of space and the atmosphere? Well, it's an arbitrary line. You could put it here, you could put it here, you could put it there. It's whatever you want to put it. You can say there's no line. I mean, there's no real hard line. It's just an arbitrary line, like the Kármán line. They just picked it. It's just arbitrary. It's not like when this molecule goes from here, this side of the line, to that side of the line, it doesn't know it passed the line. There's nothing changed about it. It's just a notional line. So this molecule isn't going to stay still. It's not float. It's going to reach say it gets kicked in a collision. It gets kicked extra hard. It goes up here, misses that one. It comes up here, it falls. Then boom, it hits this one. Then it bounces up again. Maybe bounces this way, that way. And so so you don't need a container. But now here's a bag of potato chips that you've bagged here at sea level. So there's the air density. And so the temperature is the same, density is the same number. So there's no net force. There's these guys banging from the inside, and these guys are hitting the walls from the outside. They cancel each other out. But now as we go up at altitude, the density in here or the kinetic energy is greater than here, so these guys are hitting harder, so that bag is going to want to expand and to equalize the pressure. And you can see that if you get a bag of potato chips and drive up on top of a mountain. So that's how that works. But let's take a can. Let's say we evacuate a can, so it's a vacuum. Well, it's not a total vacuum. It's got a few molecules in it. But there's fewer of these than outside, so it's going to want to crush that can Let me undo that. Z, ungroup it, arrange, ungroup. So that can is going to want to crush smaller, and then until the pressures are equal. So, and it's not going to, so the can's going to crush. But let's take this same can, put it back here, and move it way up here. Now it's the opposite here. There's more air molecules inside here than outside, so it's going to want to, the can's going to want to expand instead. Let me do it. I have to ungroup it. It's going to expand. So now, let me do that. ZZ. So let's say we open the can. So let's just open the top, or let's say we move the can. Let me ungroup that. So here it's going to clear a spot here. So here's our little can of vacuum. We clear a spot here. And so then we move the can. And remove the can. And then we're going to have a little local low pressure here. So these molecules are going to rush in and fill that spot. So yeah, you need a container here because the gradient's high. But that's not the same as, let me undo that. Up here, if you remove the can, just the opposite would happen. Remove the can, these guys are going to spread out. But they're not going to just go off into space. And so the vacuum doesn't suck. There's no suction here. And the space between this molecule and that molecule is empty, and it's no different than space up here. It's just a lot more empty space here. Where here the empty space is much smaller, but it's still empty. So there's a vacuum between each one of these molecules, whether it's just how large is the distance between them. So the vacuum, some point here in the vacuum is no different than some point here in the vacuum, other than you have to move a very small distance to reach a molecule here, where you have to move a very large distance up here. Okay, so enough of that. I probably should end the video here because I probably way exceeded the attention span. But the other thing they talk about is being able to see a lot further than you should. Here's a person standing on a curved earth. Here's another person. Here's a straight line of sight here. And notice that it gets, and say here's over water. It gets, as this person moves down here, up here, here's the line of sight. Let's say they're close together. So there's your line of sight there. But as this person walks away, further away, let me go back to here. So here's our person here. Walks further away, and they're always lined to the gravity vector. So gravity's pulling them down this way. So you go, oh, there's no gravity. Well, there's something that makes them fall to the earth. And you might think it's buoyancy, but buoyancy works. I could make a chart on that. Requires gravity to work. You can just see that in the vomit comet. When they pull 0 G's, the water doesn't stay in a glass anymore. It starts floating around. So this line of sight, these photons that are traveling from this person to that person, or let's say for this person to that person, so he could observe them. Well, let's go the other way around. This person's looking this way. The light is going to, he's looking here. He's going to try to, so this light, let me do it this way. Where do put it back here. There's this lensing effect here because the water vapor here close to the water is very dense versus up here, because here's the liquid, here's the gas, but it's not a clean line. There's some of the water molecules, not air molecules, but water molecules are above the surface, and some of them go off. You go up into space and they form clouds. So, but the density is going to be a lot less than. It's going to be highest here, so you're going to get a bending of the light. So this person's going to be able to see. Yeah, here's the light traveling this way. So this person's going to be able to see over the horizon because it's going to bend all along here, but the closer it gets to that surface, the more it's going to bend. So it bends a little bit here, and then it bends a little bit along the way, but it's going to bend a lot here. So it's going to take a circular, it's not going to go in a straight line because of the atmosphere. Now, Rob Skiba argued that that's why when the sun, their view here, and this, see, this is annoying. I'm going to make this dash sun. Text outline. Dashes. Oops. That's text. I don't want text. Outline. Fatter. They think as the sun moves around here, here's all these observers. It's going to have an angle. You can see this angle here, but this angle is going to be, but the sun's going to appear smaller than it does other places. Like he's closer, so it's going to look larger. Where this person's further away, it's going to look smaller. In fact, this person here, as it moves around, they never see it go overhead. There's no noon. They're not going to see a noontime. So they're just going to see it move. Say this person is Australia. The sun's never going to, it's always going to be in the northern hemisphere. That's because they're facing the center. It's always in the northern hemisphere, but we see that the sun's never there in the northern. And it never. Looking at top view here, shape, and see, you need to draw diagrams to see this. Words don't really capture it very well. So here's this circle here. Let me. That'll work. Home. And here's this circle. So there's your flat Earth. You think, oh, this is so boring. Nobody ever said the truth is always going to be interesting. It may be boring, the truth, but that's not the fault of the truth. That's the fault of the observer. So here's our little sun. Here's our observer here. And so he would see this, bring this to the front. He'd see the sun never let me put them. It'd be like to the north, because there's, let me draw an arrow here. There's the North Pole, so sun's to the north. And so it never be due east. There's the due east. That's west. That's west, not east. There's east. And so the sun would be rising in the east. So here's the sun coming in. But you'd never see it due east. You'd see it sort of northeast. Then it's north to the north. Then it's not a northwest. But that's not what you see. Actually, what we see when they're at the South Pole is the sun goes around and you see it go from all around. It goes from the north to the, let's see, we're moving this way, from the east to the south, to the west, to the north. So, in fact, no, it's South Pole. It's always to the north. North is this, whatever direction here is north, because you're in the bottom of the sphere. So that's what you observe. So, and then Rob Skiba's answer to this was the same thing that causes light to bend here, which they kind of scoff at. He uses that same principle here, but he calls it lensing. So lensing is just refraction. Refraction is what causes lensing. So he says lensing is, even though the sun should look smaller as it's further away, it gets refracted. So that could explain potentially why it stays larger in the one direction, but not in the other direction, because the lensing wouldn't affect the width. So that doesn't work. But actually what we see is near sunset, it's just the opposite. The lensing causes it to shrink, and so you see, instead of being a circle, you see that. So then another thing they get wrong with flat earthers is talking about line of sight rates. Here's an airplane flying, and here's constant speed, so at constant intervals of time, it went from here to here to here to here to here. And so here's the observer watching this, and so here's your line of sight, and as it moves, rotates, that's called a line of sight rate. What was here, let's say a minute later, it's here, so it moved from here to here in 1 minute. That it rotated up just that angle from here to here. So the next minute, it moves from here to here. Next minute, it moves from here to here, line of sight. Next minute, the line of sight moves to here. Then it moves to here. And notice the angle gets smaller each time. So if that's just the sun moving across, you'd see the angle would not, even if lensing caused the airplane to look bigger. So let's just say lensing makes it look bigger, so that it's big enough so that it appears the same size to its observer. Due to lensing, it's not going to change the line of sight rate. So and it's going to get smaller. So say this is 15 degrees. Earth, the sun moves 15 degrees per hour, line of sight rate. So let's say this is moving 15 degrees per minute in our airplane. Well, here it's not going to be moving 15 degrees per minute. It's going to be moving, say, half that, only 7 degrees per minute. And the limit is it's hardly moving at all. And it never gets below never goes negative unless you have diffraction or something. So yeah, it appears lower on the horizon, but because here's your, that's the angle between here, so it's higher on the horizon here, this angle, and it's lower on the horizon here, it appears that, but it's never going to go negative below the horizon. And even if lensing made it look bigger, it's not going to change the line of sight rate. And so that's another thing. Now let's move on to the next topic, and I'm covering these really fast. I spend a lot of time covering each one. So why do rockets turn? Well, if you want to go to orbit, if you take off your rocket, say this looks like Moscow, so you're going to launch a rocket from Moscow. Just, they don't do it there, but let's just say they did. And it's going to go up. If you want to go to orbit, at some point you're going to have to turn and go this way and follow the Earth around to go into orbit. So rockets have to turn to go into orbit. And then when they get into orbit, it goes around. It's falling to Earth, but it's falling to Earth at the same rate it's moving around the Earth. So that arc equals, it never hits the Earth. It's like this race car can only turn so fast, and so it has a limited turn radius. Not turn radius, but and so it follows this trajectory. Now, say when it's over here, you're coasting here with your rocket off. Say you get here and you want to do a boost burn, so you hit the burn, so you start going faster. You don't move this way, you move faster this way, and so now the rocket's going to it's going faster, so it's not going to follow that same circular orbit. It's going to follow more elliptical orbit. It's going to go way up here, then it's going to be here. It's like the top. It's like throwing a ball in the air. It's going to be, say, it's as high as it's going to go above the Earth. Now it's going to fall back toward the Earth, but it's moving this direction, so it's falling back toward the Earth. So it's going to be going fastest here and slowest here. And it's going to slow down as it goes here, and it's going to speed up. So that's just orbital mechanics. So, and then it's like, air has to push, a rocket exhaust has to push against something to make it go. Well, here's the way it works is, here's our air molecule inside here, and it's moving. And so if this were closed, it could hit here. So it's always, there's not going to be, so this thing is going to move. It's going to, equal number going to hit this one and hit this one. So there's not going to be a net force. But if you have an opening here, this one might hit here, but it won't, the other one isn't going to, it's going to pass out of here, not going to hit. And then some of them are going to be expanding and hitting here. That's going to give a push outward, but it's also going to have a component this way. So what does these air molecules push against? They push against the side of the rocket. And it's like we're in a vacuum of space. There's no vacuum inside the rocket engine. That's not a vacuum. Yeah, there's a vacuum outside of here with very few molecules. But inside here, there's no vacuum. It's really high pressure. A lot of air molecules, or whatever molecules, not air, but whatever the exhaust is. And the ones that leave the exhaust, they don't push against the rocket to make it slow down, or these push against it to make it speed up. So when it hits at this, it's going to speed it up. If it hits here, it's going to speed it up. But this was closed, when it hits there, it's going to slow it down. But it's not. It just leaves there. It's going to push against the air and affect the air. So that's another thing get wrong. Another thing, let's see how many more I got. This is the last one, is the distance. 1 over r squared. Put that in. 1 divided by r squared. So that means that once you go from here to here, whatever the intensity of the light is here, if you double it, it's going to be 1/4. So the idea is, okay, so you do that again, it's going to go down by another fourth, and by another fourth, another fourth, another fourth. But that's not the way it works. It has to double each time. So look at it this way. The next time you have to travel this much farther to go down by 1/4. And the next time you have to travel this much farther to go 1/4. Let's just do one more. The next time you have to go twice as far to get that. So we have to go to here. So you can see what's happening here. So it's not like you went to here to the next, and the next one is going to be, oops, I didn't want that. The next one, you're going to have to make this thing go this way. This far to make it go down 1/4. And the next, so you get the idea here is, so you could, that's why you could see great distances, because it's going to only go down by 1/4, but when it doubles the distance traveled before. So we can do this one more time. So we pull this to here, and zoom out further. So for, it has to move from here to here to go down another 1/4. And this goes on and on. So if this is 1 light year, it has to go out another. If this is 1 light year from here, let's say 1 light year from here to here. Then it has to go out this far. No. Yeah. Let's see. Yeah. So this far to go another light year, not another, to double it. And so this is 2 light years. It has to go double this again. You can see how this just keeps going geometrically. So at any rate, didn't explain that very well, but so these are just things that flat earthers could, if you're going to DJ again, if you're claiming to be a Christian and you want to seek the truth, and iron sharpens iron, you want to hear both sides of the arguments, not just one side, and then you can make an informed decision, not an uninformed one, and let the chips fall as they may. So this video was, once again, I kind of rushed through each one of these in this middle of the night, so it's not really a great video, but it covers issues that I don't see often covered. So let me end the video here. Zoom back in. I think I covered everything. So maybe I could get to sleep now. And I know what somebody's saying. Watching this video should put you to sleep. And I thought, yeah, maybe so. Maybe so. So maybe I ought to watch my own video. That'll probably put me to sleep. So here I am. Stop.